section 6.6, properties of kites and trapezoids. So we're still looking at quadrilaterals, four-sided polygons, but we're not looking at parallelograms. We're looking at these other types of quadrilaterals that have some properties we want to know about. So these, of course, also get added to the first page of your chapter 6 notes. So look at first at a kite. A kite is, of course, a quadrilateral, and it has exactly two pairs of congruent, congruent consecutive sides. So consecutive sides that are next to each other, and then there's two pairs of those that are congruent. So kite A, B, C, D, A, B, and A, D are congruent, B, C, and D, C are congruent, and we get some properties from that. The diagonals of a kite are always perpendicular, and there's exactly or only one pair of opposite congruent angles. Usually, not always, but usually, those are the two obtuse angles across from each other. So we're kind of using these properties to problem solve in a diagram. So first off, given kite A, B, C, D, so we know it's a kite, we have these properties to utilize if we need to. Angle DAB is 54 degrees, so DAB, label that 54, and angle CDF in here, 52 degrees. So then find the measure of angle BCD and the measure of angle ABC. So looking at what do we know, what properties we can use. So the diagonals are perpendicular. Go ahead and look at that. One pair of opposite angles are congruent. So I would think that it would be angle B, the whole angle B, angle ABC, that whole angle. And then the angle with the vertex of D, so angle ADC down here. Those would be congruent. But our properties don't say anything specifically about if we know a part, can we assume the other part? What we do know is that we have two pairs of congruent consecutive sides. So BC is congruent to DC. So triangle DBC has two congruent sides or legs. It is isosceles. And what we know about isosceles triangles is that the base angles are congruent to each other. So triangle BCD, the whole triangle, is 180 degrees. Angle BCD is 180 minus both of those 52 degree angles. So 180 minus 52 minus 52. Well, 180 minus 50 and 50. So 180 minus 100 is 80. Minus 2 again. That should leave us with 76 degrees. So angle BCD, kind of go in there and label it, 76 degrees. Now the measure of angle ABC. So we want to look at angle ABC and how much that is, okay? So triangle ABC up here, the top half, all of those angles add to 180 degrees, okay? So that 180, if we take away angle BAC and angle BCA, that will leave us with angle ABC. So this 54, we can cut it in half because we could get these two triangles, top and bottom, congruent with each other by side, side, side. So doing a little additional work, we could get this 54 to be cut in half. So we don't have anything that initially lets us say we can cut those angles in half. But if we use our triangle congruencies and some CPCDC, we could get those cut in half. So 180 minus half of 54, which is 27. And 180 minus half of 76. So half of 76 would be 38. I think 38, okay. And then go ahead and do that subtraction. 7s and 8s always throw me off, I don't know why. But doing arithmetic, growing up, learning it, like 2 plus 4, 6, that makes sense. 4 and 7, 11, that makes sense. 7 and 8, 15, okay. I don't know why. I used to have a mental block with the 7 and the 8. But 180 minus 20 and 30, so 180 minus 50 is 130. The 7 and 8 are 15, so 130, take away another 15. End up with 115 degrees. So looking at kites, looking at the properties, and then drawing upon any previous information that we need to use. So the other type of quadrilateral we want to look at is a trapezoid. Okay, so a trapezoid, you may know what it looks like. Well, let's get a formal definition that we can work with. Remember, definitions you can put on the first page of your Chapter 6 note packet. So trapezoid is a quadrilateral, so a four-sided polygon with exactly one or only one pair of parallel sides. Each of the parallel sides is called a base. And the non-parallel sides are called legs. So looking at this diagram over here, we have angle, well, I should fill this in first. So the angles at the bases, call those base angles. And then let's look at this diagram. So we have our base angles, on the top of the trapezoid. We have the base angles on the bottom of the trapezoid. So this base has two base angles. This base also has two base angles. So they're consecutive, they're next to each other, and they have that common side of the base. So two sets of base angles. Now a special type of trapezoid we're going to look at is a trapezoid where the legs, the segments that connect the bases, are themselves congruent. So think about other shapes we've looked at that have congruent legs. So we're looking at isosceles trapezoids. It's kind of like an isosceles triangle that got the top kind of cut off of it. Okay? So those legs, the remaining parts are still congruent. So if the legs of a trapezoid are congruent, then it's called an isosceles trapezoid. And it has some properties that you want to be familiar with that you can add to the first page of your note packet. So each pair of base angles are congruent. So a regular trapezoid, the base angles are just consecutive with a shared base. There's no other specific relationship. In an isosceles trapezoid, they're also congruent. If you have an isosceles trapezoid, kind of switching to a condition, a trapezoid with one pair of congruent base angles, then you can say it's isosceles. So kind of look at here the property. This one here, looking at a condition. And then here with the biconditional, we can have both a property and a condition. So a trapezoid is isosceles if and only if you see that biconditional wording. If and only if the diagonals are congruent. So that one can go either way. If it's a trapezoid that's isosceles, then the diagonals are congruent. Other way, if it's a trapezoid with congruent diagonals, then it's isosceles. So some more information for you to look at isosceles trapezoids and really problem solve with if you run into that kind of information in a problem.